Hello, everyone, and welcome to today's webinar. My name is Chris Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Dr. Corey Packard. Dr. Packard is a Principal Engineer and Director of Research, Engineering, and Product Management here at Thermal Analytics. He has more than 20 years of experience in remote sensing and physics-based simulation, with his primary technical focus being EOIR signature prediction. Other technical efforts of Dr. Packard involve field test validations, phenomenological investigations, software development support, and predicting the behavior of optical sensor systems in turbulent atmospheres from space-based platforms. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar, and we'll be sending you the link following this presentation. And with that, Corey, if you're ready, you may begin.
Great. Thanks, Chris. Welcome, everyone, to today's webinar. We'll be discussing high-fidelity satellite simulation, and we'll be talking about thermal and electrical simulation, as well as EOIR sensor radiance predictions, all with MuSES. So I'm going to go ahead and get started with a bit of an agenda for today's webinar. I'm going to start out by sharing some motivation for performing this sort of satellite simulation work. And then I'm going to describe a methodology that we've developed for performing dynamic thermal simulation of orbiting satellites. I'll talk a bit about how we incorporate solar panels and battery cells into our coupled thermal electrical satellite simulation efforts. And then we'll describe a bit the prediction of both battery lifetime and solar panel degradation over the course of the mission lifetime of a satellite. We'll be presenting both temperature and EOIR signature results for both LEO and GEO orbital scenarios. And then we'll be describing a bit of a sensitivity study on how different model variations impact the average signature of a satellite. And then we'll wrap up with some conclusions. Okay, so there's a variety of motivations for performing this sort of satellite simulation. Starting on the thermal side of things, satellites can suffer from thermal problems due to the extremes of the environment that they're in, as well as the high power density of their design with all the electronic components being packed on the inside and outside. Additionally, the lifetime of the battery pack and the degradation of the solar panel over time can both be concerns depending on the intended duration of the mission. And thermal electrical simulation can help with these two concerns by helping ensure that the temperature extremes of the critical components of the satellite stay within acceptable operating ranges during the orbit. Also validating the power budget by incorporating the temperature dependent performance of the battery and efficiency of the solar panels, and making sure that works with the electrical components that are on board and need to be powered to fulfill the mission of the satellite. Then going beyond that, this sort of simulation can help determine the impact of battery lifetime and solar panel degradation on the mission lifetime of the satellite. And then going beyond just the thermal to the IR side of things, we've seen that the characterization of satellites has grown in importance as the costs of launching objects into space has gotten more accessible than ever, and the number of resident space objects has greatly increased in recent years. So there's a lot of things in orbit, and a lot of different scientific and security agencies are interested in knowing what all is orbiting. And so these sorts of groups benefit from the ability to predict the signature of resident space objects under various conditions, but doing so requires a sophisticated methodology that we're going to be discussing here. And this sort of predictive capability is especially important for things like uncooperative targets, agencies that lack the appropriate surveillance that make testing either a challenge or an impossibility, and thus requiring a CAE-based approach. So first I want to start out with just a quick review of the thermal physics that we want to make sure that we consider and incorporate into our methodology. So when we've got an orbiting satellite, we're interested in the thermal radiation exchange between the satellite and Earth, between the satellite and space, as well as the internal radiation and conduction that's going on with the satellite system itself. In addition to that, we've got both directed and reflected solar loading, and all these things are important factors and need to be included. So we will be using MuSES for all the analysis that will be presented today. So first I wanted to talk just briefly about what MuSES is as it pertains to today's webinar. So MuSES is a transient thermal solver and EOIR rendering tool. And as you can see on the right there, the inputs are 3D mesh geometry, and then we apply to that various thermal material properties, heat sources, environmental and boundary conditions, and that lets us then perform our thermal simulation where we predict the physical temperature of all the surfaces of the satellite system. And then we can go a step beyond that and predict what that satellite system would look like to an EOIR sensor. And this can be done in a band integrated way or a hyperspectral way. We can consider specular and diffuse surfaces and derive a variety of metrics from these sensor images that we radiometrically generate. So this slide kind of shows an overview of some of the different aspects of satellite simulation that can be accomplished with MuSES. We can incorporate solar panels and multi-cell battery packs, internal, external electronics. We can look at the signature of the satellite after we predict its temperature and perform electrical simulations at the same time in a coupled fashion. And finally, we can look at terrestrial scenes from an overhead perspective if we want, and generate images of ground-based scenes from a satellite perspective. We accomplish this using a cotherm process, and cotherm is another tool that accompanies MuSES, and this lets us set up an automated process that can exchange data with different tools. And in this case, you see this block diagram form of the tool. So what it allows us to do is bring in a propagated orbit from a third-party tool, use that to specify the environmental parameters in a dynamic fashion for the satellite that we're going to be simulating. We can visualize the orbit, perform the transient thermal and electrical simulation, generate IR renderings if we want, create a variety of different post-processing graphs and animations and things to understand the results and make decisions based on those. So this is a quick description of the communication satellite model that we'll be using for today's demonstrations. So we see the 3D geometry of the satellite with the deployed solar panels in the lower left there. Each color represents different parts of the satellite. So the satellite has a variety of electrical components, and we see some of the more important ones labeled on the right there, both internal and exterior electronic components. And if you look at the power draw of all those components and you add it up, you get that red graph that's in the middle of the slide there, showing the total component power draw. So that's the power draw that's required by this satellite to fulfill its mission, and you can see it kind of changing throughout the orbit itself. So helping to power these electronics, we have a number of solar panels that are deployed on each side, and we see sort of a multi-layer stack up here that we're using to represent this solar panel. So we've got a thin solar cell, and then it's got a carbon fiber layer, and then between that and the rear facing carbon fiber layer, we've got an aluminum honeycomb that's providing some internal structure. So that gives you some information on both the power source side of things as well as the power sink, where that power is going to go. And of course, there's an internal battery pack as well with a number of cells, and that battery is going to get charged when there's excess sunlight, and then that battery will be used to power the electronics during the eclipse. So when we perform a thermal simulation, it's important to look at these different optical surface properties for radiation exchange purposes. And so we need solar absorptivity and thermal emissivity for our dual band radiation solver. And so the table in the upper left shows those two properties for some of the important different optical surfaces of the satellite itself. And then the geometry that you see at right is colored based on which material and thus which optical surface has been applied to each of those. And the picture in the lower left kind of shows the sort of inspiration for this model with black surfaces and silver and gold and orange and white and so forth. Okay, so we're going to start by looking at a LEO scenario, kind of inspired by a Starlink kind of an orbit. So we're using a two-line element from a Starlink satellite, and then we're propagating that for a duration of 6 hours with a orbital position every 60 seconds. So every minute of that 6 hours, we've got a different position of the satellite. And the graphics at the right help you visualize what that orbit looks like. There's an animation showing the satellite going around the Earth. In the upper right, there's a graph that kind of shows the periods of time when the satellite is illuminated by the sun and when it's in shadow from the Earth. And then in the lower right, we see what the satellite looks like from the perspective of the sun, and then one with the satellite reference frame fixed with a yellow arrow kind of pointing at the sun. So a few different ways that you can kind of visualize and understand the orbit. And we'll be looking a little more closely at two particular times of this orbit, at 3:45 and 4:30. And in the upper right, you can see an orange and black dashed line that indicate those two times, one being a sunlit time and one being an eclipsed or shadowed time. And we see in the lower left what the solar flux on the satellite looks like at those two times. So when we perform our transient analysis, we can see not only what the solar flux on the satellite is, but also what the resultant surface temperatures are on the satellite at those two times. And so the four graphics on the right-hand side of the slide demonstrate that. So the top two images there are for the 3:45 and 4:30 times from one particular perspective or vantage point of the satellite. And then the bottom two graphics are same two times, but from a different perspective. So looking from underneath the satellite. So this just gives some initial solar and thermal results from the satellite. But as I mentioned, we can integrate multi-cell battery packs and solar panels into MuSES simulations. And we do that by coupling the electrical and thermal solutions automatically. And this is done because the electrical and thermal parts of the problem are dependent on one another. And so we simulate them together to make sure we accurately capture that interdependence. So what's happening in the system, which you can see in the upper right, you see the satellite with a kind of a cutaway view showing the internal battery cells as well as the external solar panels. So the solar panels are generating power when the satellite is sunlit. That's used to power the components and charge the batteries when appropriate. The battery is then going to charge and discharge as necessary, depending on whether there's enough sunlight to run the components or whether the battery needs to supplement that. And so we see a variety of different thermal electrical quantities in the 6 subplots on the right. In panel A there, we see the average temperature of the solar panel oscillating as it goes in and out of the sun. Then moving to the right there, we see the temperature of the battery. In this case, the temperature of the battery is going up during the simulation because we did not employ any sort of thermal management on the battery itself. We just kind of let it do what it was going to do to kind of show a baseline configuration. Panel C, we see the pack current of the battery, and that is positive when it's being charged and negative when it is discharging during the eclipse periods. Then moving down to the lower row there, we see the efficiency of the solar panel, and that's changing because even though there's a nominal efficiency around 29 or 30%, the actual efficiency of the, one second here. Okay, the actual efficiency of the solar panel is affected by the incidence angle of the sun, by the temperature of the panel, and that's why the efficiency changes in a dynamic or transient way, because it's not a static number. In panel E, we see a few different interesting quantities. The green line there shows the power that's harvested from the solar panels. The red curve shows that total power draw of all those components, and then the blue is the resultant power that's going to the battery. Again, positive when the battery is being charged by excess sunlight, and negative when it's being discharged during the eclipse periods. And then finally, we have in panel F, the oscillating state of charge of the battery. And so it's going up when the battery is being charged, going down when it's being discharged. So we can see the charge-discharge cycle in a dynamic fashion. And last thing I'll mention here is that we can use a variety of methods to model the electrical portion of the solar panel and battery pack, including equivalent circuits. So here's kind of a quick summary of both the thermal and electrical results of these simulations. So we see those same thermal electrical subpanels on the left, and then some animations of surface temperature as the orbit time changes on the right. Okay, so as I mentioned earlier, we can also predict and incorporate things like battery lifetime and solar panel degradation. And so here we see that MuSES can predict how the solar panel efficiency changes with things like panel temperature, which I described before, solar incidence angle, and also the degradation of the solar panel over its lifetime. And in addition to this, MuSES can predict how battery pack performance degrades over the lifetime of the mission as well. And that's due to two primary factors. The first being aging, which is referred to as calendar fade, and the next is referred to as cycling fade, which has to do with the usage pattern of the battery. And so both of these are deleterious effects that are negative impacts on the performance of the system. And so the four subplots that you see at the bottom of this slide show how these two effects can be incorporated at the same time. So we see a family of three curves in all of these plots. And so each of those curves, the different colors, represent a multi-orbit transient simulation, but they're done at three different times during the course of the satellite's mission lifetime. The first green line, that's the uppermost line there, that's done at t=0. So right after the satellite launch, basically it's showroom condition. Nothing has degraded yet. The blue line that's in the middle is after 3 years. And then the red line at the bottom is a little over 7 years. And so what has happened is, as the solar panel has been exposed to the extreme environments of space, and you've got proton and electron fluence and things like that happening, the efficiency of the solar panel is degraded over time. That means it can generate less power than it could when it was new. In addition, when you look at the battery, the capacity of the battery goes down over time, and the internal resistance of the battery goes up over time. All of those are negative effects, and when you combine them all together, we can see that in panel D, when the satellite is new, when it starts from an assumed 50% initial charge, we can see how it charges up to full capacity, and there's no issues. But by the time, almost 7.5 years go by, the red curve there, we see the state of charge going down, meaning the system is no longer sustainable. The load of the different electronic components is too much for the overall PV battery system in its degraded state. And I should mention here before I go too far, that in the lower left, you see kind of the light gray there. There's some references to some of the different publications that we've come out with in the last few years that describe these different things in more detail, if you want a bit more detailed information on the highlights that I'm showing here. Okay, so now transitioning away from the thermal side and talking a bit about the IR side of things. The graphic in the upper left is something that we've presented before, where you bring in your model into MuSES, you set up the different parts with their materials and thermal properties and heat sources, then you apply weather data and mission profile, predict physical temperatures, as you see in the middle image there, and then finally predicting what that system would look like to a remote sensor. And we've demonstrated and validated this for a variety of different applications, including ground, sea, air, human personnel. And so today we'll be talking about the addition of satellites into this target modeling process. There's a variety of different space domain awareness scenarios that one might be interested in for orbital remote sensing, including a space-to-space scenario where you've got a satellite that's being observed from another orbiting platform. There's the Earth-based scenario where you've got an Earth-based observatory of some sort looking up through the atmosphere at orbiting objects. And then finally, an overhead persistent scenario where you're using an orbiting platform to look down at a terrestrial scene. And we're going to start here by looking at a space-to-space engagement scenario. And we're going to do that with the help of 3 different virtual sensor perspectives that are going to be used to evaluate the signature of the satellite from these different views to kind of have a more holistic approach. The graphics that you see on the right-hand side there, we've got the sensor view A, which is directly beneath the satellite, kind of looking up at it, normal to the solar panels, and then 2 other views, view B and C, where there's a slight negative and slight positive sensor elevation angle. And for those 2, we're going to actually change the sensor azimuth as well, a full 360 degrees, to generate kind of a holistic look at the signature of the satellite from many different perspectives. And so, whereas before during the thermal simulation, the 2 properties for radiation exchange that are critical is a band average solar absorptivity value and a band average thermal emissivity value. When we do these radiometric sensor renderings, it's important to have spectral optical surface properties because we're going to be doing spectral calculations. And so what you see in these 3 plots is the emissivity, diffuse reflectivity, and specular reflectivity of some of the different optical coatings that are on the satellite itself, including the MLI and so forth. And these are going to be important in the results that I show to come here. And as I said, we're going to show a bit of a sensitivity study. And to that end, the table in the lower right there shows the different model variants that we're going to be seeing results for. So we've got a baseline model, and the rest will be compared against this one. That's the baseline communication satellite. We've got a model that we're calling off, and in this case, all the components are inactive. They're unpowered. So they're not drawing any power, which means the solar panels are not generating any power. We've got a model where we've replaced the silver and gold MLI with black MLI. We've got one where the Earth-facing backing layer of the solar panel array has been coated in silver instead of black. We've got one where the nominal efficiency of the PV panel, which was 29%, has been reduced to a nominal value of 19%, so that we can see how that degradation of the solar panel affects its signature over time. You know, whether the aging of the satellite is visible to a sensor. And then finally, one where we've increased the thickness of that internal honeycomb layer of the solar panel, which adds thermal mass to the system. Okay, so for starters, we're going to look at the average long wave radiance of the satellite from that perspective of the sensor that's just below, looking straight up at it, which you can see in the upper right. Those I'll include those diagrams to help you remember which sensor perspective we're using to look at which results. So we see some interesting things here. We see a family of curves where each different colored curve represents a different model variant, where the thick black line is the baseline satellite. The red line that's highest at the peaks is the off model. Some other interesting ones here that we see is the green line that shows the thicker PV model. As we've increased the thermal mass of the system, the amplitude of the oscillation is lower than the others. You know, because of that increased thermal mass, it's heating slower and cooling slower. And then finally, we see the blue line that's at the bottom with the silver PV backing. Because it's has such a high reflectance in this band, we're seeing the reflection of the space environment having a big factor in how this appears to the sensor. And so the surface temperature of the solar panel is kind of being concealed a bit because of the reflective nature of the coating that we've put on it. And just to make sure this is clear, the way that we're calculating these curves is we're generating these 2D radiometric sensor images at many different times throughout the orbit for all these different models. The images look like what I'm showing at the right there. I just showed two, one with the off model and one with the baseline. And then we're averaging all the pixels that are on the satellite to come up with that average long wave radiance. So each data point on the family of curves on the left is a pixel-wise average of these radiometric images like you see on the right. In the midwave, we see something similar to the long wave, with one kind of notable exception that sticks out, which is these big spikes that you see at various times throughout the transient simulation. And these kind of anomalies are due to solar glints, where the geometric relationship between the sun, that kind of crinkly, reflective MLI blanket that's on the bus of the satellite, and the sensor are all aligned perfectly, where we get this specular reflection of the solar energy being focused right towards the sensor of interest. And so those big radiant spikes are coming from solar glints. And I've got some images above the family of curves there to show renderings of the satellite when that solar glint is present and when it's not. So you can see how that affects the average signature and drives it up. Okay, so this is just a summary of the last two that I showed with the mid-wave and the long wave results, and some of the reasons why we saw those, due to some surfaces have higher thermal emissivities and some having lower thermal emissivities, one model having higher thermal mass, and so forth. So we can see the effect of these different design choices that you might have and how that affects the signature of the satellite. Now we're going to start looking at the other two sensor perspectives. And as I said, we're going to move the sensor in 360 degrees around the satellite from that elevation angle, so we can get a kind of a holistic look at it. And so we're going to present these results using these polar plots. And so we see two different polar plots here, one on the left being at 345, which is the sunlit scenario, and the one on the right being 430, which is the eclipsed time of the orbit. So we see something kind of interesting here, which is on the left, you see the purple line has the greatest average radiance in the long wave. And that's the black MLI model. So the bus of the satellite has been covered with a black MLI, which is a higher solar absorptivity. So it's heating up and it's got a high thermal emissivity that's facing the sensor as well. And from this vantage point, the bus is a more central part of the signature of the satellite, and the effect of the solar panels is a bit reduced just because of the perspective of the sensor. So now we see that having kind of a big effect. If we look at the positive 15-degree angle, we see something kind of similar, and we can see how the ranking in terms of radiance from biggest to smallest in an average sense changes depending on when it's sunlit or when it's eclipsed and so forth. So this gives you an idea of how you can evaluate comprehensively the signature of an orbiting platform. In the midwave, We see these spikes again. On the left, you see those big radiant spikes that are coming from solar glints, but obviously they are absent on the lower right, and that's because that's the 4:30 time that's eclipsed. So there's no solar and thus no solar glints that are showing up then. And from the positive 15-degree angle, we see something a bit similar. Okay, I want to talk a bit next about Earth-based space domain awareness. And whereas we were looking at a space scenario before, now we're going to look at an Earth-based scenario. We've got an observatory on Earth that's looking up through the atmosphere at an orbiting object. And we're going to use a GEO scenario for this. That's kind of inspired by the GO-17. So we've got another multi-hour orbit where we're propagating it with 60-second sampling. And the graph in the lower right shows the portion that is illuminated, and then there's a period where it's in shadow, and then it goes back to being illuminated. And for reference, I will say the simulations that we ran here in the GEO case, we ran several days of simulation, due to the longer time period of the orbit. But we're just showing the results from the kind of one of the more interesting snippets of the orbit that has the shadow period in it. Okay, so the graphic that we see on the lower left shows the surface temperatures for some of the important Earth-facing components of the baseline on satellite and the off satellite model. So again, we've got the baseline on and off model that we're comparing here. And because we're going to be looking from the Earth up, we're looking at the components on the outside that are facing the Earth, because those are the ones that are going to be contributing most heavily to the signature, the average signature of the satellite. So one of the things that you notice here, all in these different colors represent different components on the satellite. The solid lines are all the baseline on model, and all the dotted or dashed lines correspond to the off model, where the components are unpowered and the PV panel is not generating any power. And what we see is that the temperature of all the surfaces from the on model, the baseline model, are warmer than their counterparts on the off model, with one key exception, which is the solar panel. And the reason for that is that when the satellite is operating, the solar panel is converting absorbed solar energy into electrical power. And that's being done at some efficiency, which we've discussed before, some non-zero efficiency. When the components are off and the solar panels are not generating any power, their efficiency is effectively zero. So all the absorbed solar is going into thermal energy rather than electrical energy. And that is then going to increase the temperature of those solar panels. And that's why we see the temperature of the solar panels being higher for the off case, whereas for all the other components, because they're being powered, they're warmer when they're on, which makes sense. But what effect does this have on the signature of the satellite? Well, first we look at some renderings of the satellite. I've shown 4 here. I've shown 2 when the satellite is being sunlit, and 2 when it's in its eclipse state. And then on the left, we have the on case, and on the right, we have the off case. So if you look carefully, you can see that the components are warmer for the on case than the off case in that central satellite bus. But if we look at the deployed solar panels, you see that they're warmer in the off case, and that's because of the efficiency being zero, as I previously described. So how do these 2 kind of conflicting phenomenon, how do they contribute to the average radiance? Well, if we look at the average radiance of this GEO satellite from the perspective of the Earth, I've plotted it here in that black dotted line represents the off model, and the red curve is the baseline on satellite. And we see that the off model actually has a larger signature, average signature, from this perspective than the on model. And that's because those solar panels are so big and dominate the average, that because they're warmer for the off model, the average is higher. Now, In that central period during the eclipse, we see that trend reverse, and that's because with the on model, those components are still powered. So in the off model, they start cooling off when the sun goes away. In the off model, there's still some power being generated. So we see a little bit of reversal of polarity there. And then once the sun again is illuminating the satellite, we see the other trend emerge. Now, just for reference, on a secondary axis in blue there, I'm showing a visible band average radiance with those open circles. And what you notice is that during that eclipse period in the middle, kind of between 8:30 and 9:30, you see that the average visible radiance is 0, it flatlines. And that's because satellite's not being illuminated and there's no signature. However, there is still a temperature of the satellite. So it's still emitting energy, it's reflecting. And so there's still a trackable, discernible signature of the satellite during the eclipse period in the long wave infrared, whereas visible tracking is going to be extremely difficult. And we can see that if we calculate the delta radiance between the on and off curves. So if we subtract the red curve from the black curve, we see the difference that's caused by the operational state of the satellite. And we can see that even during that eclipse period, at almost every time during that, there is a non-zero delta radiance between the two, which means not only is the signature of the satellite observable, but it's a discernible difference between the two. And I won't go into detail here, but if you look at that reference in the lower right, we published a paper earlier this year where we talked about how discernible that would be, what the signal to noise ratio might be, how easy it might be for a telescope or something else to be able to actually identify whether you're looking at an on or an off satellite. So pretty interesting result there. Okay, so I'm going to finish up with some conclusions here. I think what we've shown today is that MuSES can be used to accurately predict the dynamic temperatures of orbiting payloads. We've shown some validation data in the past, but what we've shown here is the ability for satellite designers to make sure that key components of the system are going to stay within acceptable temperature limits, and you can make sure that the passive and active thermal control systems that you've included are doing their job in managing critical temperatures appropriately. We've shown how you can integrate solar panels and multi-cell battery packs into your transient thermoelectrical simulations and look at power budget and charging and discharging. We've also demonstrated how you can incorporate the effects of battery lifetime and solar panel degradation and see how that's going to affect the performance of the satellite in future years. And then moving beyond the thermal and electrical and looking at the signature side of things, we've explored both Earth-based and space-based engagement scenarios that you might be interested in for space domain awareness. We've explored LEO and GEO scenarios during this talk and shown how those can be simulated and the kind of interesting results that can come from those. We've shown how you can take the thermal results from a coupled thermal electrical simulation and then translate those over into remote sensor predictions in thermal infrared wave bands, mid-wave and long wave. And we use that communication satellite to demonstrate that. And then we showed how you can use a variety of different vantage points of virtual sensors to come up with a comprehensive evaluation of the average signature of the satellite. And then we've shown how you can use model variants to see how different choices of materials or choices of thermal mass or differences in the operational state of the satellite can impact the average satellite signature. And again, as I've said, there's a few different public publications that we've come out with that have more detail on each of these things. And with that, I'll wrap up and thank you for your attention and participation in today's webinar.
All right, thank you, Corey. Let's get to some questions. Have you looked into lunar simulations at all?
Yeah, that's a good question. So we've had a few people express interest in lunar simulations. We have looked into it a bit. We've started developing an approach for accurately predicting the temperature of the lunar surface and for objects that might be on the lunar surface, and are looking into developing an approach similar to what you've seen here for the LEO and GEO, but for lunar orbit scenarios. So it's a active area of research that we hope to present on before too long.
Excellent, thank you. The import of geometries are in which format?
Yeah, good question. So there's a variety of formats that MuSES can ingest. OBJ wavefront files is one, PadTran, NASTran, neutral files. Yeah, there's a variety of different file formats, and we can send information on that for sure.
Thank you. Can we give the attitude of solar panels in addition of satellite attitude?
Do you mean can that be supplied? Yeah, that's another active area that I haven't presented on in this webinar, but before too long we'll be presenting a scenario where we're changing the attitude of the solar panels so that they can kind of track the sun and optimize the harvesting of solar energy and have those rotating separately from the satellite. So that will be a demonstration that will be coming before too long as well.
Excellent. What orbital tools can supply propagated paths to your cotherm process?
Yeah, okay, yeah. So as I mentioned, we're using a cotherm process to kind of perform this automation of the process and data exchange and graphing and animations and all that stuff. There are a few different tools that can supply the needed information. It's a pretty simple file format that we're using in the cotherm process. So there's probably a number of tools. The ones that we've been focused on and have used recently include FreeFlyer, which is a tool from a company called AI Solutions. We've also worked with STK and taken STK exported data and fed it in, as well as like SGP4, which is I believe a free Python-based tool. So yeah, there's a number of different orbital tools that can generate the needed data.
Thank you. The renders appear to be ideal response. Can sensor noise be added to the EOIR simulated images?
Yes, excellent question. That's very true. In pretty much all the renderings that I showed, we turned off sensor noise. But yes, sensor noise can be included, as can sensor blur. That would be from diffraction and things like that. So both of those can be excluded or included based on user preference. And yep, so that's an option that you can certainly deploy if you're interested in increasing the realism of your sensor.
Excellent, thank you. What has Thermoanalytics published in regards to orbiting satellites?
Yeah, okay, so let's see. We had 4 publications this year and 2 last year. Last year at ICES, which was in Calgary, we published a thermal validation for a simple CubeSat model against previously published data on that CubeSat. So that was a thermal validation, and then we had a signature publication at the AMOS conference in the fall of last year. This year, we again had another signature publication at AMOS. We had 2 publications at SPIE in the UK, one focusing on satellite signatures and the other focusing on the impact of directed energy weapons on orbiting satellites. And we also had a publication at the SmallSat conference in August this year, and that was focused on battery lifetime and solar panel degradation and ways to kind of optimize performance there.
All right, well, Thank you, Corey. Looks like that that does it for questions. So that will complete today's webinar. We appreciate you all for attending. You will all receive a follow-up email this afternoon containing links to download the presentation slides, as well as watch the recorded webinar session. Again, thank you, Corey, and thank you all, and everyone have a nice day.